We start part 4 with a bunch of definitions. These definitions are fairly helpful when we're thinking about basic probability questions like the ones you had on the worksheet on Thursday. So probability applies to trials or experiments where we don't know exactly what the outcome is going to be. We have something random happening. There needs to be a single outcome at the end, and what we really kind of want to pay attention to in this little section is this idea of a sample space and an event. So a sample space is every possible outcome, where an event is some subset of those possible outcomes. And we'll usually denote these with capital letters when we talk about the actual sets themselves. And then eventually we're going to get into our probability notation, which I find the most important part of this beginning section, this idea that if we want to talk about the probability of A occurring, we can use this notation here. It does not mean P times A, it's the probability of A occurring. So we have our first example. Suppose you're rolling 2 dice. What is the sample space? Well, our sample space, remember, we're going to note with a big capital S, as it says up here. And we're going to use our set notation. So we do that curly Q bracket. And this says, okay, what are the possibilities if you're rolling 2 dice? Well, I could roll snake eyes, right? That's a possibility. I could roll a 1 and then a 2. Could be a 1 and a 3. It's good to have some sort of structure when you're doing things like this. And then you could continue on. And we can fill out the entire sample space like this. As you can see right now, there are a total of 36 possibilities when you're rolling your die. So let's assume that the first of this ordered pair is the first die, and the second is the second die. So we could have our snake eyes all the way through to having, I don't know, like a 5 on the first die and a 3 on the second die. But that's not the same thing as getting a 3 on the first and a 5 on the second. Those are distinct and different events. There are 2 ways to roll an 8 using a 3 and a 5 when it comes to dice. All right, so if we want to keep going and start talking about some events, we can define our events. So event A is the event of rolling 2 dice who sum to 7. So now we're going, okay, well, what are dice that sum to 7? 1 and 6, 2 and 5, 3 and 4. And all of these could happen the other way as well. There are 2 ways because there are 2 dice that each of these could happen. So 4, 3, 5, 2, and 6, 1. Those are all the ways that we could roll a 7. We can actually see all of those along this diagonal here. All right, and then B, it says, is the event of rolling doubles, which means we get the same number on both dice. So this could be our 1s, pair of 2s, pair of 3s, pair of 4s, pair of 5s, or pair of 6s. This is our other diagonal. All right, so this is basically how we talk about event spaces. I have never asked a question about event spaces, but they are very useful when you're setting up basic probabilities to think about what's going on. Because when we talk about the classic approach to probability, the probability of an event is just how many ways that A can happen over how many ways the outcomes could happen in general. So for our example, the probability of A, well, there were 6 different ways to roll a 7 out of the total of 36 ways to our total outcome that we could get when we roll 2 dice. So there's a 1 in 6 chance of rolling a 7. Whereas the probability of B has the same probability. There were 6 ways to roll doubles out of the 36 possibilities. So those are our probabilities. This classic approach really does rely on you having these sample spaces. So we can think back to the first example on the worksheet from Thursday about we had 400 people. Ooh, that's a giant pen. That's not what I wanted. We had 400 people getting put into the treatment group. We had 500 people getting put into the control group. And then we asked, what's the probability of being in the treatment group? Well, there are 400 people or 400 ways to get put into the treatment group. And there are a total of 900 things that could happen, right? So you could actually think of this, the probability or the treatment category would just be treatment 400 times, right? Whereas our sample space would have been treatment 400 times and then control 500 times. So there would have been 900 things in the sample space, 900 things that could have happened, possible outcomes, and 400 there. So that's how you got this 4 over 9 for that first problem. is just basic, classic probability approaches. Now, biggest, most important thing here, only possible when we're talking about things that are equally likely. So rolling a die, picking randomly people for this treatment versus control, those are the only times that this is actually going to be useful. There are two other types of probability, neither of which really matter to us in part 4, but I'm going to quickly talk about. The first one is empirical probability, sometimes called frequentist probability. This is actually what's at the heart of everything we do in part 6, 7, 8, everything else in this class. And this is the idea that the proportion of times a phenomenon will occur in a very long series of repetitions is just a good estimate of our probability. So if it's something we don't actually know the outcome to, if we don't know that a coin is fair, right? A good strategy is to just take that coin and flip it a ton of times and see what happens. How often does it come up heads? So if you're not sure, if you're not flipping, if you have a coin and you're not sure it's fair or not, this is the strategy to use this empirical probability. This is just like observed probability as opposed to the more mathy, like what is the actual true probability. So we have this example here. If you're tossing a coin, on a fair coin, we know it's 50-50 chance, right? Whoa, yellow pen still. 50% chance, right? Or 1/2 or 0.5, all the same thing. If you toss one coin, do you know whether you'll get a head or a tail? No. It's random. That's why we have this probability in the first place. It's 50-50. If you toss a coin 100 times, do you know how many heads you'll get? The answer is still no, right? We don't know how many heads. But now it's not a complete crapshoot. We expect 50 heads, right? So this is the big deal, is that we kind of have this expectation that it should be around 50% of the time getting heads. So if there's 100 tosses, it should be around 50. And our last question here says, well, what if you got 80 heads out of those 100 tosses? Would you think that's a fair coin? And this is where we're going to move in the course later, is can we say definitively that this is not a fair coin? Can we say statistically that this is not a fair coin? Because 80 out of 100 is not at all close to 50 out of 100. And we even saw in that one example for the Kahoot, especially if you were in the second class, we actually went ahead and did it in StatCrunch, that out of 1,000 times, we never got 200 of 300 or more showing up heads. So we could do this in StatCrunch, and I assure you, this is going to be a probability of around 0 that this would happen. So this all depends on the law of large numbers. You can see here a little applet that's showing you tossing a coin and how many, the probability of heads. So toss one coin, turns out we get out heads. So based on empirical probabilities, probability of heads, 1 out of the 1 times, 100%, as you can see. So we're going, okay, 100% chance this has heads. At this point, I don't know there's another side. Looks like we flipped the coin again. And now we're down here at 50%. So out of the 2, this time unless it come up tails, we now think it's a 50% chance. And you can see how this continues on. The next time it looks like they ended up getting another head. So now it's a 2 out of 3. Right? It just keeps bouncing around. But eventually, when we get out to a larger number of trials, it's very, very unlikely that we're far away from that 50%. We are going to see around 50%. And that is the law of large numbers, that the more repetitions you do, the closer we're going to be to the real value. The bigger our sample is, the better we can feel about our estimate. Which is about, I think, what we talked about in the second class when we talked about that coin problem. The more we have, the closer things should be together. The last type of probability is a subjective approach. This is just our feelings, right? Based on facts or whatever knowledge you might have. So I always throw this ridiculous one here. What's the probability the Chargers will make the playoffs? And everybody is going to have their own number here based on their own knowledge of the NFL, their own personal biases about the Chargers, such and such. So I won't even answer this one, but there are 3 types of probability. We focus in part 4 on subjective, on the classic, and the subjective and the empirical are kind of left to the wayside.